Hello, everyone. Well, I want to talk today about observer theory. It's based on a piece I wrote a little while ago, which I'm going to go through. I happen to be working on something that's a kind of a follow-on to this right now, so I thought this would be an opportunity to go through what I wrote a little while ago. So, we're talking about observer theory. The concept of the observer. We call it perception. We call it measurement. We call it analysis. But in the end, it's about how we take the world as it is and derive from it the impression of it that we have in our minds. We might have thought that we could do science sort of purely objectively, without any reference to observers or their nature. But what we've discovered, particularly dramatically in our physics project, is that the nature of us as observers is critical even in determining the most fundamental laws we attribute to the universe. But what ultimately does an observer, say like us, do? And how can we make a theoretical framework for it? Much as we have a general model for the process of computation instantiated by something like a Turing machine, we'd like to have a general model for the process of observation, a general observer theory. Central to what we think of as an observer is the notion that the observer will take the raw complexity of the world and extract from it some reduced representation suitable for a finite mind. There might be zillions of photons impinging on our eyes, but all we extract is the arrangement of objects in a visual scene. Or there might be zillions of gas molecules impinging on a piston, yet all we extract is the overall pressure of the gas. In the end, we can think of it fundamentally as being about equivalencing. There are immense numbers of different individual configurations for the photons of the gas molecules that are all treated as equivalent by an observer who's just picking out the particular features needed for some reduced representation. There's, in a sense, a certain duality between computation and observation. In computation, one's generating new states of a system. In observation, one's equivalencing together different states. That equivalencing must, in the end, be implemented underneath by computation. But in observer theory, what we want to do is just characterize the equivalencing that's achieved. For us as observers, it might in practice be all about how our senses work, what our biological or cultural nature is, or what our technological devices or structures we've built are. But what makes a coherent concept of observer theory possible is that there seem to be general abstract characterizations that capture the essence of different kinds of observers. It's not immediately obvious that anything suitable for a finite mind could ever be extracted from the complexity of the world. And indeed, the principle of computational equivalence implies that computational irreducibility and its multi-computational generalization will be ubiquitous. But within computational irreducibility, there must always be slices of computational reducibility. And it's these slices of reducibility that an observer must try to pick out and that ultimately make it possible for a finite mind to develop a useful narrative about what happens in the world that allows it to make decisions, predictions, and so on. How special is what an observer does? At its core, it's just about taking a large set of possible inputs and returning a much smaller set of possible outputs. And certainly that's a conceptual idea that's appeared in many fields under many different names: a contractive mapping, reduction to a canonical form, a classifier, an acceptor, a forgetful functor, evolving to an attractor, extracting statistics, model fitting, lossy compression, projection, phase transitions, generalization, group transformations, and so on. But here we want to think not about what's mathematically describable, but instead about what in general is actually implemented, say by our senses, our measuring devices, or our ways of analyzing things. At an ultimate level, everything that happens can be thought of as being captured by the Ruliad, the unique object that emerges as the entangled limit of all possible computations. And in a vast generalization of ideas like that, our brains, like any other material thing, are made of atoms. So too, any observer must be embedded as some kind of structure within the Ruliad. But a key concept of observer theory is that it's possible to make conclusions about an observer's impression of the world just by knowing about the capabilities and assumptions of the observer without knowing in detail what the observer is like inside. And so it is, for example, that in our physics project, we seem to be able to derive essentially from the structure of the Ruliad the core laws of 20th century physics, general relativity, quantum mechanics, and the second law, just on the basis of two features of us as observers: that we're computationally bounded and that we believe we're persistent in time, even though underneath we're made of different atoms of space at every successive moment. And we can expect that if we were to include other features of us as observers, for example, that we believe there are persistent objects in the world, or that we believe we have free will, then we'd be able to derive more aspects of the universe as we experience it, or more natural laws we attribute to it. But the notion of observers and observer theory isn't limited purely to physical observers. It applies whenever we try to get an impression of something. And so, for example, we can also operate as mathematical observers, sampling the Ruliad to build up conclusions about mathematical laws. Some features of us as physical observers, like the computational boundedness associated with the finiteness of our minds, inevitably carry over to us as mathematical observers. But other features do not. But the point of observer theory is to provide a general framework in which we can characterize observers and then see the consequences of those characterizations for the impressions or conclusions observers will form. The operation of observers. As humans, we have senses like sight, hearing, touch, taste, smell, and balance. And through our technology, we also have access to a few thousand other kinds of measurements. So how basically do these all work? The vast majority, in effect, aggregate a large number of small inputs to generate some kind of average output, which in the case of measurements is often specified as a real number. In a few cases, however, there's a discrete choice between output that's made on the basis of whether the total input exceeds a threshold. So think distributed consensus schemes, weighing balances, and so on. But in all cases, what's fundamentally happening is that lots of different input configurations are all being equivalenced, or more operationally, the dynamics of the system essentially make all equivalent states evolve to the same attractor state. So as an example, let's consider measuring the pressure of a gas. There are various ways to do this, but a very direct one is just to have a piston and see how much force is exerted by the gas on this piston. So where does this force come from? At the lowest level, it's the result of lots of individual molecules bouncing off the surface of the piston, each transferring a tiny amount of momentum to it. If we looked at the piston at an atomic scale, we'd see it temporarily deform from every molecular impact. But the crucial point is that at a large scale, the piston moves together as a single rigid object, aggregating the effects of all those individual molecular impacts. But why does it work this way? Essentially, it's because the intermolecular forces inside the piston are much stronger than the forces associated with molecules in the gas. Or put more abstractly, there's more coupling and coherence inside the observer than between the observer and what it's observing. We see the same basic pattern over and over again. There's some form of transduction that couples the individual elements of what's being observed to the observer. Then within the observer, there's something that in essence aggregates all these small effects. Sometimes that aggregation is directly numerical, as in the addition of lots of small momentum transfers, but sometimes it's instead more explicitly like evolution to one attractor rather than another. So consider, for example, the case of vision. An array of photons fall on the photoreceptor cells on our retinas, generating electrical signals transmitted through nerve fibers to our brains. Within the brain, there's then effectively a neural net that evolves to different attractors depending on what one's looking at. Most of the time, a small change in input image won't affect what attractor one evolves to. But much like with a weighing balance, there's an edge at which even a small change can lead to a different output. One can go through lots of different types of sensory systems and measuring devices, but the basic outline seems to always be the same. First, there's a coupling between what is being sensed or measured and the thing that's doing the sensing or measuring. Quite often that coupling involves transducing from one physical form to another, say from light to electricity or force to position. Sometimes then the crucial step of equivalencing different detailed outputs is achieved by sort of simple numerical aggregation, most often by accumulation of objects, atoms, raindrops, and so on, or physical effects, forces, currents, and so on. But sometimes the equivalence is instead achieved by a more obviously dynamical process. It could amount to simple amplification in which, say, the presence of a small element of input, say an individual particle, tips over some metastable system so that it goes into a certain final state. Or it could be more like a neural net, where there's a more complicated translation defined by sort of hard to describe borders between basins of attraction leading to different attractors. But okay, so what's the end point of a process of observation? Ultimately, for us humans, it's an impression created in our minds. Of course, that gets into lots of slippery philosophical issues. Yes, each of us has an inner experience of what's going on in our mind, but anything else is ultimately an extrapolation. We make the assumption that other human minds also see what we see, but we never can feel it from the inside. We can, of course, make increasingly detailed measurements, say, of neural activity to see how similar what's going on is between one brain and another. But as soon as there's the slightest structural or situational difference between the brains, we really can't say exactly how their impressions will compare. But for our purposes in constructing a general observer theory, we're basically going to make the assumption, or in effect, philosophical approximation, that whenever a system does enough equivalencing, that's tantamount to it acting like an observer, because it can then act as a front end that takes the incoherent complexity of the world and collimates it to the point where a mind will derive a definite impression from it. Of course, there's still a lot of subtlety here. There has to be just enough equivalencing or not too much. For example, if all inputs were always equivalent to the same output, there'd be nothing useful observed. And in the end, there's somehow got to be some kind of match between the compression of input achieved by equivalencing and the capacity of the mind that's ultimately deriving an impression from it. A crucial feature of anything that can reasonably be called a mind is that something's got to be going on in there. It can't be, for example, that the internal state of the system is fixed. There has to be some internal dynamics, some computational process that we can identify as the ongoing operation of the mind. At an informational level, we might say that there has to be more information processing going on inside than there is flow of information from the outside. Or in other words, if we're going to be meaningful observers like us, we can't just be bombarded by input we don't process. We have to have some capability to think about what we're seeing. All of this comes back to the idea that a crucial feature of us as observers is that we are computationally bounded. We do computation. That's why we can have an inner sense of things going on. But the amount of computation we do is tiny compared to the computation going on in the world around us. Our experience represents a heavily filtered version of what's happening outside. And the essence of being an observer like us is that we're effectively doing lots of equivalencing to get that filtered version. But we can imagine a future in which we kind of expand our minds. Well, can we think about that? Perhaps we encounter some alien intelligence with a fundamentally less constrained mind. Well, at some point there's an issue with this, because in a sense, the idea that we have a coherent existence relies on us having limited minds. For without such constraints, there wouldn't be a coherent self that we could identify with coherent inner experience. Let's say we're shown some system, say in nature, from the outside. Can we tell if there's an observer in there? Ultimately not, because in a sense, we'd have to be inside that observer and be able to experience the impression of the world that it's getting. But in much the same way as we extrapolate to believing that, say, other human minds are experiencing like we're experiencing, so also we can potentially extrapolate to say what we might think of as an observer. And the core idea seems to be that an observer should be a subsystem whose internal states are affected by the rest of the system, but where many external states lead to the same internal state, and where there is rich dynamics within the observer that in effect operates only on its internal states. Ultimately, following the principle of computational equivalence, both the outside and the inside of the observer subsystem can be expected to be equivalent in the computations they're performing. But the point is that the coupling from outside the subsystem to inside effectively coarse-grains what's outside so that the inner computation is operating on a much reduced set of elements. Why should any observer subsystems exist? Presumably at some level it's inevitable from the presence of pockets of computational reducibility within arbitrary computationally irreducible systems. But more important for us is that our very existence And the possibility of our coherent inner experience depends on us operating as observers. And almost as a self-fulfilling prophecy, our behavior tends to perpetuate our ability to successfully do this. For example, we can think of us choosing to put ourselves in situations and environments where we can predict what's going to happen well enough to survive as observers. At a mundane practical level, we might do this by not living in places subject to unpredictable natural forces, or by doing things like building ourselves structures that shelter us from those forces. So we've talked about observers operating by compressing the complexities of the world to inner impressions suitable for finite minds. And in typical situations that we describe as perception and measurement, the main way this happens is by fairly direct equivalencing of different states. But in a sense, there's a higher level story that relies on formalization and, in essence, computation, and that's what we usually call analysis. Let's say we have some intricate structure, perhaps some nested fractal pattern. A direct rendering of all the pixels in this pattern ultimately won't be something well suited for a finite mind. But if we gave rules or a program for generating the pattern, we'd have a much more succinct representation of it. But now there's a problem with computational irreducibility. Yes, the rules determine the pattern, but to get from these rules to the actual pattern can require an irreducible amount of computation. And to reverse engineer the pattern to find the rules can require even more computation. Yes, there are particular cases, like repetitive and simple nested patterns, where there's enough immediate computational reducibility that a computationally bounded system or observer can fairly easily do the analysis and get the compression. But in general, it's hard. And indeed, in a sense, it's the whole mission of science to pick away at the problem and to try to find more ways to reduce the complexity of the world to human-level narratives. Computational irreducibility limits the extent to which this can be successful, but the inevitable existence of pockets of reducibility, even within computational irreducibility, guarantees that progress can always in principle be made. As we invent more kinds of measuring devices, we can extend our domain as observers. And the same is true when we invent more methods of analysis or identify more principles in science. But the overall picture remains the same. What's crucial to being an observer is equivalencing many states of the world, either through perceiving or measuring only specific aspects of them, or through identifying simplified narratives that capture them. In effect, perception and measurement tend to do lossy compression. Analysis is more like lossless compression, where the equivalencing is effectively not between possible inputs, but between possible generative rules. How observers construct their perceived reality. Our view of the world is ultimately determined by what we observe of it. We take what's out there in the world and, in effect, construct our perceived reality by our operation as observers. Or in other words, insofar as we have a narrative about what's going on in the world, that's something that comes from our operation as observers. And in fact, from our physics project, we led to an extreme version of this, in which what's out there in the world is just the whole Ruliad. And in effect, everything specific about our perceived reality must come from how we operate as observers, and thus how we sample the Ruliad. But long before we get to this ultimate level of abstraction, there are lots of ways in which our nature as observers builds our perceived reality. Think about any material substance, like a fluid. Ultimately, it's made of lots of individual molecules doing their thing. But observers like us aren't seeing those molecules. Instead, we're aggregating things to the point where we can just describe the system as a fluid that operates according to the narrative defined by the laws of fluid mechanics. But why do things work this way? Ultimately, it's the result of the repeated story of the interplay between underlying computational irreducibility and the computational boundedness of us as observers. At the lowest level, the motion of the molecules is governed by simple laws of mechanics. But the phenomenon of computational irreducibility implies that to work out the detailed consequences of running these rules involves an irreducible amount of computational work, which is something that we as computationally bounded observers can't do. And the result of this is that we'll end up describing the detailed behavior of the molecules as just random. Well, I've talked about at length elsewhere this is the fundamental origin of the second law of thermodynamics. But for what we're talking about here, the important point is that it's what makes observers like us construct the reality of things like fluids. Our computational boundedness as observers makes us unable to trace all the detailed behavior of molecules and leaves us content to describe fluids in terms of the narrative defined by the laws of fluid mechanics. Our physics project implies that the same kind of story with physical space. For in our physics project, space is ultimately made of a network of relations or connections between discrete atoms of space that's progressively being updated in what ends up being a computationally irreducible way. But we, as computationally bounded observers, can't decode all the details of what's happening, and instead we end up with a simple aggregate narrative that turns out to correspond to continuum space operating according to the laws of general relativity. The way both coherent notions of matter or fluids and space-time emerge for us as observers can be thought of as a consequence of the equivalencing we do as observers. In both cases, there's immense and computationally irreducible complexity underneath, but we're ignoring most of that by effectively treating different detailed behaviors as equivalent, so that in the end, we get to a comparatively simple narrative more suitable for our finite minds. But we should emphasize that what's really going on in the system is something much more complicated. It's just that we as observers aren't paying attention to that, so our perceived reality is much simpler. Okay, but what about quantum mechanics? In a sense, that's an extreme test of our description of how observers work and the extent to which the operation of observers constructs their perceived reality. So let's talk about the case of quantum mechanics. In our physics project, the underlying structural hypergraph that represents space and everything in it is progressively being rewritten according to definite rules. But the crucial point is that at any given stage, there can be lots of ways this rewriting can happen. And the result is that there's a whole tree of possible states of the universe that can be generated. So given this, why do we ever think that definite things happen in the universe? Why don't we just think that there's an infinite tree of branching histories for the universe? Well, it all has to do with our nature as observers and the equivalencing we do. At an immediate level, we can imagine looking at all those different possible branching paths for the evolution of the universe. And the key point is that even though they come from different paths of history, two states can just be the same. Sometimes it'll be obvious that they're the same. Sometimes we might have to determine, say, whether two hypergraphs are isomorphic. But the point is that to an observer, at least one that isn't managing to look at arbitrary implementation details, the states will inevitably be considered equivalent. But now there's a bigger point. Even though from the outside, there might be a whole branching and merging multi-way graph of histories for the universe, observers like us can't trace that. And in fact, all we perceive is a single thread of history. Or said another way, we believe that we have a single thread of experience, something closely related to our belief that despite the changing underlying elements from which we're made, we are somehow persistent in time, or at least during the span of our existence. But operationally, how do we go from all those underlying branches of history to our perceived single thread of history? We can think of the states on different threads of history as being related by what we can call a branchial graph that joins states that have immediate common ancestors. And in the limit of many threads, we can think of these different states as being laid out in branchial space. In traditional quantum mechanics, this layout defines kind of a map of quantum entanglements, with each piece of common ancestry representing an entanglement between states. In physical space, whether we're looking at molecules in a fluid or atoms of space, we can think of us operating as observers who are physically large enough to span many underlying discrete elements, so that what we end up observing is just some kind of aggregate average result. And it's very much the same kind of thing in branchial space. We as observers tend to be large enough in branchial space to be spread across an immense number of branches of history, so that what we observe is just aggregate averaged results across all those branches. There's lots of detailed complexity in what happens on different branches, just like there is in what happens to different molecules or different atoms of space. And the reason is that there's inevitably computational irreducibility, or in this case, more accurately, multi-computational irreducibility. But as computationally bounded observers, we just perceive aggregate results that average out the underlying apparent randomness to give a consistent single thread of experience. And effectively, this is what happens in the transition from quantum to classical behavior. Even though there are many possible detailed quantum threads of history that an object can follow, what we perceive corresponds to a single consistent aggregate classical sequence of behavior. And this is typically true even at the level of our typical observation of molecules and chemical processes. Yes, there are many possible threads of history for, say, a water molecule, but most of our observations aggregate things to the point where we can talk about a definite shape for the molecule with definite chemical bonds and so on. But there's a special situation that actually looms large in typical discussions of quantum mechanics. We can think of it as being the result of doing measurements that aren't aggregating threads of history to get an average, but are instead doing something more like a weighing balance, always tipping one way or the other. In the language of quantum computing, we might say that we're arranging things to be able to measure a single qubit. In terms of the equivalencing of states, we might say that we're equivalencing lots of underlying states to specific canonical states like spin up and spin down. Why do we get one outcome rather than the other? Ultimately, we can think of it all depending on the details of us as observers. So to see this, let's start from the corresponding question of physical space. We might ask why we observe some particular thing happening. Well, in our physics project, everything about what happens is deterministic. But there's still the arbitrariness of where we are in physical space. We'll always basically see the same laws of physics, but the particulars of what we'll observe depend on where we are, say on the surface of the Earth versus in interstellar space, and so on. Is there a theory for where we are? In some sense, yes, because we can go back and see why the molecules that make us up landed in the particular place where they did. But what we can't have we can't have an external theory for is just which molecules end up making up us as we experience ourselves from the inside. In our view of physics and the universe, it's in some sense the only ultimately subjective thing where our internal experience is situated. And the point is that basically, even though it's much less familiar, the same thing is going on at the level of quantum mechanics. Just as we happen to be at a certain place in physical space, so we're at a certain place in branchial space. Looking back, we can trace how we got there, but there's no a priori way to determine where our particular experience will be situated. And this means we can't know what kind of the local branchial environment will be. And so, for example, what the outcome of sort of balance-like measurements will be. Just as in traditional discussions of quantum mechanics, the mechanics of doing the measurement, which we can think of as effectively equivalencing many different underlying branches of history, will have an effect on subsequent behavior and subsequent measurements. But let's say we just look at the level of the underlying multi-way graph, or more specifically, the multi-way causal graph that records causal connections between different updating events. Then we can identify a complicated web of interdependence between events that are time-like, space-like, and branch-like separated. And this interdependence seems to correspond precisely to what's expected from quantum mechanics. In other words, even though the multi-way graph is completely determined, the arbitrariness of where the observer is, particularly in branchial space, combined with the inevitable interdependence of different aspects of the multi-way causal graph, seems sufficient to reproduce the not quite purely probabilistic features of quantum mechanics. Well, in making observations of physical space, it's common to make a measurement at one place or time, then make another measurement at another place or time, and, for example, see how they're related. But in actually doing this, the observer will have to move from one place to the other and persist from one time to another. And in the abstract, it's not obvious that that's possible. For example, it could be that an observer won't be able to move without changing, or in other words, that pure motion won't be possible for an observer. But in effect, this is something that we as observers assume about ourselves. And indeed, as I've talked about actually elsewhere, this is a crucial part of why we perceive space-time to operate according to the laws of physics we know. But what about in branchial space? we have much less intuition for this than physical space, but we still effectively believe that pure motion is possible for us as observers in branch-Hill space. It could be like an observer in physical space, say near a space-time singularity, that an observer would get shredded when trying to move in branch-Hill space. But our belief is that typically nothing like that happens. At some level, being at different locations in branch-Hill space presumably corresponds to picking different bases for our quantum states, or effectively to defining our experiments differently. And somehow our belief in the possibility of pure motion in branch-Hill space seems related to our belief in the possibility of making arbitrary sequences of choices in sets of experiments we do. Observers of abstract worlds. We might have thought that the only thing ultimately out there for us to observe will be our physical universe. But actually, there are important situations where we're essentially operating not as observers of our familiar physical universe, but instead of what amount to abstract universes. And what we'll see is that the ideas of observer theory seem to apply there too, except that now what we're picking out and reducing to internal impressions are features not of the physical world, but of abstract worlds. Our physics project, in a sense, brings ideas about the physical and abstract worlds closer, and the concept of the Ruliad ultimately leads to a deep unification between them. For what we now imagine is that the physical universe as we perceive it is just the result of the particular kind of sampling of the Ruliad made by us as certain kinds of observers. And the point is that we as observers can make other kinds of samplings, leading to what we can describe as abstract universes. And one particularly prominent example of this is mathematics, or rather metamathematics. Imagine starting from all possible axioms for mathematics, then constructing the network of all possible theorems that can be derived from them. We can consider this as forming a kind of metamathematical universe. And the particular mathematics that some mathematician might study, we can think of as the result of a mathematical observer observing that metamathematical universe. There are both close analogies and differences between this and the experience of a physical observer in the physical universe. Both ultimately correspond to samplings of the Ruliad, but somewhat different ones. In our physics project, we imagine that physical space and everything in it is ultimately made up of discrete elements that we identify as atoms of space. But in the Ruliad in general, we can think of everything being made up of pure atoms of existence that we call ems. In the particular case of physics, we interpret these ems as atoms of space, but in metamathematics, we can think of ems as corresponding to kind of sub-axiomatic elements of symbolic structures from which things like axioms or theorems can be constructed. A central feature of our interaction with the Ruliad for physics is that observers like us don't track the detailed behavior of all the various atoms of space. Instead, we equivalence things to the point where we can get descriptions that are reduced enough to fit in our minds. And something similar is going on in mathematics. We don't track all the individual sub-axiomatic ems, or usually in practice even the details of fully formalized axioms and theorems. Instead, mathematics typically operates at a much higher and more human level, dealing not with questions like how real numbers can be built from ems or even axioms, but rather with what can be deduced about the properties of mathematical objects like real numbers. In the physics analogy to the behavior of a gas, typical human mathematics operates not at the molecular level of individual ems or even axioms, but rather at the fluid dynamics level of human accessible mathematical concepts. In effect, therefore, a mathematician is operating as an observer who equivalences many detailed configurations, ultimately of ems, in order to form higher-level mathematical constructs suitable for our computationally bounded minds. And while at the outset one might have imagined that anything in the Ruliad could serve as a possible mathematics, the point is that observers like us can only sample the Ruliad in particular ways, leading to only particular possible forms for human accessible mathematics. It's a very similar story to the one we've encountered many times in thinking about physics. In studying gases, for example, we could imagine all sorts of theories based on tracking detailed molecular motions. But for observers like us, with our computational boundedness, we inevitably end up with things like the second law of thermodynamics and the laws of fluid mechanics. And in mathematics, the main thing we end up with is higher level mathematics, mathematics that we can do directly in terms of typical textbook concepts, rather than constantly having to drill down to the level of axioms or eames. In physics, we're usually particularly concerned with issues like predicting how things will evolve through time. In mathematics, it's more about accumulating what can be considered true. And indeed, we can think of an idealized mathematician as going through the Ruliad and collecting in their minds a kind of bag of theorems or axioms that they consider to be true. And given such a collection, they can essentially follow the entailment paths defined by computations of the Ruliad to find more theorems to add to their bag. And yes, if they put a false theorem, then because a false premise in the standard setup of logic implies everything, they'll end up with an infinite explosion of theorems that won't fit in a finite mind. So in observing the physical universe, we talk about our different possible senses like vision, hearing, and so on, or different kinds of measuring devices. In observing the metamathematical universe, the analogy is basically different possible kinds of theories or abstractions, say algebraic versus geometrical versus topological versus categorical, and so on, with new approaches being like new kinds of measuring devices. Particularly when you think in terms of the Ruliad, we can expect a certain kind of ultimate unity in the mathematical universe, but different theories and different abstractions will pick up different aspects of it, just as vision and hearing pick up different aspects of the physical universe. But in a sense, observer theory gives us a global way to talk about this and to characterize what kinds of observations observers like us can make, whether of the physical universe or the metamathematical one. In physics, we've seen then that in our physics project, how this allows us to find general laws that describe our perception of the physical world and that turn out to reproduce the core known laws of physics. In mathematics, we're not as familiar with the concept of general laws, though the very fact that higher level mathematics is possible is presumably in essence such a law, and perhaps the kinds of regularities seen in areas like category theory or others as the inevitable dualities we expect to be able to identify between different fields of mathematics. All these laws ultimately rely on the structure of the Ruliad, but the crucial point is that they're not talking about the raw Ruliad. Instead, they're talking about just certain samplings of the Ruliad that can be done by observers like us and that lead to certain kinds of internal impressions in terms of which these laws can be stated. Mathematics represents a certain kind of abstract setup that's been studied in a particularly detailed way over the centuries, but it's not the only kind of abstract setup we can imagine. And indeed, there's even a much more familiar one, the use of concepts and words in human thinking and language. We might imagine that at some time in the distant past, our forebears could signify, say, rocks only by pointing at individual ones. But then there emerged the general notion of rock captured by a word for rock. And once again, this is a story of observers and equivalences. When we look at a rock, it presumably produces all sorts of detailed patterns of neuron firings in our brains, different for each particular rock. But somehow, presumably essentially through evolution to an attractor in the neural net in our brains, we equivalence all these patterns to extract our inner impression of the concept of a rock. In the typical tradition of quantitative science, we tend to be interested in doing measurements that lead to things like numerical results. But in representing the world using language, we tend to be interested instead in creating symbolic structures that involve collections of discrete words embedded in a grammatical framework. Such linguistic descriptions don't capture every detail. In a typical observer kind of way, they broadly equivalence many things, and in a sense reduce the complexity of the world to a description in terms of a limited number of discrete words and linguistic forms. Within any given person's brain, there'll be thoughts defined by patterns of neuron firings, and the crucial role of language is to provide a way to robustly package up those thoughts and, for example, represent them with discrete words so they can be communicated to another person and unpacked in that person's brain to produce neuron firings that reproduce what amount to those same thoughts. When we're dealing with something like a numerical measurement, we might imagine that it could have some kind of absolute interpretation. But words are much more obviously an arbitrary basis for communication. We could pick a different specific word, say from a different human language, but still communicate the same thing. All that's required is that everyone who's using the word agrees on its meaning. And presumably that normally happens because of shared social history between people who use a given word. It's worth pointing out that for this to work, there has to be a certain separation of scales. The collective impression of the meaning of a word may change over time, but that change has to be slow compared to the rate at which the word is used in actual communication. In effect, the meaning of a word, as we humans might understand it, emerges from the aggregation of many individual uses. In the abstract, there might not be any reason to think that there'd be a way to understand words consistently. But it's a story very much like what we've encountered in both physics and mathematics. Even though there are lots of complicated individual details underneath, we as observers manage to pick out features that are simple enough for us to understand. In the case of molecules in a gas, that might be the overall pressure of the gas. And in the case of words, it's a stable notion of meaning. Put another way, the possibility of language is another example of observer theory at work. Inside our brains, there are all sorts of complicated neuron firings, but somehow these can be packaged up into things like words that form human-level narratives. There's a certain complicated feedback loop between the world as we perceive it and the words we use to describe it. We invent words for things we commonly encounter, chair, table, and so on. Yet once we have a word for something, we're more able to form thoughts about it or communicate about it. And that in turn makes us more likely to put instances of it in our environment. In other words, we tend to build our environment so that the way we have of making narratives about it works well, or in effect, so our inner description of it can be as simple as possible, and it can be as predictable to us as possible. We can view our experience of physics and of mathematics as being the result of us acting as physical observers and mathematical observers. Now we're viewing our experience of the conceptual universe as being the results of us acting as conceptual observers. But what's crucial is that in all these cases, we have the same intrinsic features as observers: computational boundedness and a belief in persistence. The computational boundedness is what makes us equivalence things to the point where we can have symbolic description of the world, for example, in terms of words. And the belief in persistence is what lets those words have persistent meanings. And actually, these ideas extend beyond just language to paradigms and general ways of thinking about things. When we define a word, we're in effect defining an abstraction for a class of things. And paradigms are somehow a generalization of this, ways of taking lots of specifics and coming up with a uniform framework for them. And when we do this, we're in effect making a classic observer theory move and equivalencing lots of different things to produce an internal impression that's simple enough to fit in our finite minds. In the end, it's all just the Ruliad. Our tendency as observers is always to believe that we can separate our inner experience from what's going on in the outside world. But in the end, everything is just part of the Ruliad. And at the level of the Ruliad, we as observers are ultimately made of the same stuff as everything else. But can we imagine that we can point at one part of the Ruliad and say that's an observer, and another part and say that's not? At least to some extent, the answer is presumably yes, at least if we restrict ourselves to observers like us. But it's a somewhat subtle and seemingly circular story. For example, one core feature of observers like us is that we have a certain persistence, or at least we believe we have a certain persistence. But inevitably, at the level of the raw Ruliad, we're continually being made from different atoms of existence, i.e. different eames. So in a sense, in what sense are we persistent? Well, the point is that an observer can equivalence those successive patterns of eames so that what they observe is persistent. And yes, this is, at least on the face of it, circular. And ultimately, to identify what parts of the Ruliad might be persistent enough to be observers, we'll have to ground this circularity in some kind of further assumption. What about the computational boundedness of observers like us, which forces us to do lots of equivalencing? At some level, that equivalencing must be implemented by lots of different states evolving to the same states. But once again, there's circularity, because even to define what we mean by the same states, are isomorphic graphs the same and so on, we have to be imagining certain equivalencing. So how do we break out of the circularity? The key is presumably the presence of additional features that define observers like us. And one important class of such features has to do with scale. We're neither tiny nor huge. We involve enough EAMs that consistent averages can emerge, yet we don't involve so many EAMs that we span anything but an absolutely tiny part of the whole Ruliad. And actually, a lot of our experience is determined by our size as observers. We're large enough that certain equivalencing is inevitable, yet we're small enough that we can reasonably think of there being many choices for where we are. The overall structure of the Ruliad is a matter of formal necessity. There's only one possible way for it to be. But there's contingency in our character as observers. And for example, in a sense, there's a fundamental constant in nature as we perceive it, which is our extent in the Ruliad, say measured in EAMs, and appropriately projected in the physical space, branchial space, and so on. And the fact that this extent is small compared to the whole Ruliad means that there are many possible observers who can think of existing at different positions in the Ruliad. And those different observers will look at the Ruliad from different points of view and thus develop different internal impressions of perceived reality. But a crucial fact central to our physics project is that there are certain aspects of that perceived reality that are inevitable for observers like us and that correspond to core laws of physics. But when it gets to more specific questions, what does the night sky look like from where you are, and so on, different observers will inevitably have different versions of perceived reality. So is there a way to translate from one observer to another? Essentially, that's a story of motion. What happens when an observer that's at one place in the Ruliad moves to another place? Inevitably, the observer will be made of different EAMs if it's at a different place. But will it somehow still be the same? Well, that's a subtle question that depends both on the background structure of the Ruliad and the nature of the observer. If the Ruliad is too wild, think space-time near a singularity, then the observer will inevitably be shredded as it moves. But computational irreducibility implies a certain overall regularity to most of the Ruliad, making pure motion at least conceivable. But to achieve pure motion, the observer still has to be made of something that is somehow robust, essentially some lump of computational reducibility that can predictably survive the underlying background of computational irreducibility. In space-time, we can identify such lumps with things like black holes and particles like electrons and photons and so on. And yes, in our models, there's probably considerable commonality between black holes and particles. It's not yet clear quite what the analog is in branchial space, though a very simple example might involve persistence of qubits. And in Ruliad space, one kind of analog is the very notion of concepts. For in effect, concepts, as represented, for example, by words, are the analog of particles in Ruliad space. They are the robust structures that can move across Ruliad space and maintain their identity, carrying the same thoughts to different minds. So what does all this mean for what can constitute an observer in the Ruliad? Observers, in effect, leverage computational reducibility to extract simplified features that can fit in finite minds. But observers themselves must also embody computational reducibility in order to maintain their own persistence and the persistence of the features they extract. Or in other words, observers must, in a sense, always correspond to patches of regularity in the Ruliad. But can any patch of regularity in the Ruliad be thought of as an observer? Probably not usefully so, because another feature of observers like us is that we are connected in some kind of collective social framework. Not only do we individually form internal impressions in our minds, but we also communicate those impressions. And indeed, without such communication, we wouldn't, for example, be able to set up things like coherent languages with which to describe things. What we assume about ourselves. So a key implication of our physics project and the concept of the Ruliad is that we perceive the universe to be the way we do because we are the way we are as observers. And the most fundamental aspect of observers like us is that we're doing lots of equivalencing to reduce the complexity of the world to internal impressions that fit in our minds. But just what kinds of equivalencing are we actually doing? At some level, a lot of that is defined by the things we believe or assume about ourselves and the way we interact with the world. A very central assumption we make is that we're somehow stable observers of a changing outside world. Of course, at some level, we're not actually stable at all. We're built up from EAMs whose configuration is changing all the time. But our belief in our own stability, and in effect, our belief in our persistence in time, makes us equivalence those configurations. And having done that equivalencing, we perceive the universe to operate in a certain way that turns out to align with the laws of physics we know. But actually, there's more than just our assumption of persistence in time. For example, we also have an assumption of persistence in space. We assume that at least on reasonably short timescales, we're consistently observing the universe from the same place and not, say, continually darting around. The network that represents space is continually changing around us. But we equivalence things so that we can assume that in a first approximation, we're staying in the same place. Of course, we don't believe that we have to stay in exactly the same place all the time. We believe we're able to move. And here we make what amounts to another assumption of stability. We assume that pure motion is possible for us as observers. In other words, we assume that we can go to different places and still be the same us, with the same properties as observers. At the level of the raw Ruliad, it's not at all obvious that such assumptions can consistently be made. But as we discussed before, the fact that for observers like us, they can, at least to a good approximation, that they can do this, at least to a good approximation, is a reflection of certain properties of us as observers, in particular of our physical scale being large in terms of atoms of space, but small in terms of the whole universe. Related to our assumption about motion is our assumption that space exists, or that we can treat space as something coherent. Underneath, there's all sorts of complicated dynamics of changing patterns of Eames, but on the timescales at which we experience things, we can equivalence these patterns to allow us to think of space as having a coherent structure. And once again, the fact that we can do this is a consequence of physical scales associated with us as observers. In particular, the speed of light is fast enough that it brings information to us from the local region around us in much less time than it takes our brain to process it. And this means that we can equivalence all the different ways in which different pieces of information reach us, and we can consistently just talk about the state of a region of space at a given time. Part of our assumption that we're persistent in time is that our thread of experience is at least locally continuous, with no breaks. Yes, we're born and we die, and we also sleep. But we assume that at least on scales relevant for our ongoing perception of the world, we experience time as something continuous. More than that, we assume that we have just a single thread of experience, or in other words, that there's always just one us going through time. Of course, even at the level of neurons in our brains, all sorts of activity goes on in parallel, but somehow in our normal psychological state, we seem to concentrate everything so that our inner experience follows just one thread of history on which we can operate in a computationally bounded way and form definite memories and have definite sequences of thoughts. We're not as familiar with branchial space as with physical space, but presumably our fundamental assumption of stability extends there as well. And when combined with our basic computational boundedness, it then becomes inevitable, as we talked about before, that we'll conflate different quantum paths of history to give us as observers, a definite sort of classical thread of inner experience. Well, beyond stability, another very important assumption we implicitly make about ourselves is what amounts to an assumption of independence. We assume that we can somehow separate ourselves off from everything else. And one aspect of this is that we assume we're localized and that most of the Ruliad doesn't matter to us, so that we can equivalence all the different states of the rest of the Ruliad. But there's also another aspect of independence, that in effect we can choose to do whatever we want, independent of the rest of the universe. And this means we can assume that we can, for example, essentially do any possible experiment, make any possible measurement, or go anywhere we want in physical or branchial space, or indeed Rulial space. We assume that we effectively have free will about these things, determined only by our inner choices and independent of the state of the rest of the universe. Ultimately, of course, we're just part of the Ruliad, and everything we do is determined by the structure of the Ruliad and our history within it. But we can view our belief of freedom as a reflection of the fact that we don't know a priori where we'll be located in the Ruliad. And even if we did, computational irreducibility would prevent us from making predictions about what we will do. So beyond our assumptions about our own independence from the rest of the universe, there's also the question of independence between different parts of what we observe. And quite central to our way of parsing the world is our typical assumption that we can think about different things separately. In other words, we assume that it's possible to factor what we see happening in the universe into independent parts. In science, this manifests itself in the idea that we can do controlled experiments in which we study how something behaves in isolation from everything else. It's not self-evident that this will be possible, and indeed in areas like ethics, it might fundamentally not be. But we as observers tend to implicitly assume it. And actually, we normally go much further because we typically assume that we can describe and think about the world symbolically. In other words, we assume that we can take all the complexity of the world and represent at least the parts of it that we care about in terms of discrete symbolic concepts of the kind that appear in human or computational language. There's lots of detail in the world that our limited collection of symbolic concepts doesn't capture, and effectively equivalences out. But the point is that it's this symbolic description that normally seems to form the backbone of the inner narrative we have about the world. There's another implicit assumption that's being made here, however. It's that there's some kind of stability in the symbolic concepts we're using. Yes, any particular mind might parse the world using a particular set of symbolic concepts, but we make the implicit assumption that there are other minds out there that work like ours. And this makes us imagine that there can be some form of objective reality that's just always out there to be sampled by whatever mind might happen to come along. Not only, therefore, do we assume our own stability as observers, we also assume a certain stability to what we perceive of everything that's out there. Underneath, there's all the wildness and complexity of the Ruliad, but we assume that we can successfully equivalence things to the point where all we perceive is something quite stable and something that we can describe as ultimately governed by consistent laws. It could be that every part of the universe just does its own thing with no overall laws tying everything together. But we make the implicit assumption that no, the universe, at least as far as we perceive it, is a more organized and consistent place. And indeed, it's that assumption that makes it possible for us to operate as observers like us at all, and even to imagine that we can usefully reduce the complexity of the world to something that fits in our finite minds. The cost of observation. What resources does it take for an observer to make an observation? In most of traditional science, observation is at best added as an afterthought, and no account is taken of the process by which it occurs. And indeed, for example, in the traditional formalism of quantum mechanics, while measurement can have an effect on a system, it's still assumed to be an indivisible act without any internal process. But in observer theory, we're centrally talking about the process of observation. And so it makes sense to try asking questions about the resources involved in this process. We might start with our own everyday experience. Something happens out in the world. What resources and, for example, how much time does it take us to form an impression of it? Let's say that out in the world, a cat either comes into view or it doesn't. There are signals that come into our brain from our eyes, effectively carrying data on each pixel in our visual field. Then inside our brain, these signals are processed by a succession of layers of neurons, with us in the end concluding either there's a cat there or there's not. And from artificial neural nets, we get a pretty good idea of how this likely works. And the key to it, as we talked about before, is that there's an attractor. Lots of different detailed configurations of pixels all evolve either to the cat or no cat final state. The different configurations have been equivalents so that only a final conclusion survives. The story is a bit trickier, though, because cat or no cat really isn't the final state of our brain. Hopefully, it's not the last thought we have. Instead, our brain will continue to think more thoughts. So cat, no cat is at best some kind of intermediate waypoint in our process of thinking, sort of an instantaneous conclusion that we'll continue to build on. And indeed, when we consider measuring devices, like a piston measuring the pressure of a gas, we similarly usually imagine that they will come to an instantaneous conclusion, but continue operating and producing more data. How long should we wait for each intermediate conclusion? How long, for example, will it take for the stresses generated by a particular pattern of molecules hitting a piston to dissipate out and for the piston to be ready to produce more data? There are lots of specific questions of physics here, but if our purpose is to build a formal observer theory, how should we think about such things? There is something of an analogy in the formal theory of computation. An actual computational system, say in the physical world, will just keep computing. But in formal computation theory, it's useful to talk about computations that halt and about functions that can be evaluated and give a definite answer. So what's the analog of this in observer theory? Instead of general computations, we're interested in computations that effectively implement equivalences. Or put another way, we want computations that destroy information, that have many incoming states, but few outgoing ones. As a practical matter, we can either have the outgoing states explicitly represent whole equivalence classes, or they can just be canonical representatives, like in a network where at each step, each element takes on whatever the majority or consensus value of its neighbors was. But however it works, we can still ask questions about what computational resources were involved. How many steps did it take? How many elements were involved? And with the idea that observers like us are computationally bounded, we can expect limitations on these resources. But with this formal setup, we can start asking just how far an observer like us can get, say in coming to a conclusion about the results of some computationally irreducible process. An interesting case arises in putative quantum computers. In the model implied by our physics project, such a quantum computer effectively performs many computations in parallel on the separate branches of a multi-way system representing the various threads of history of the universe. But if the observer tries to come to a conclusion about what actually happened, they have to knit together all those threads of history, in effect by implementing equivalences between them. One could in principle imagine that an observer who just would one could in principle imagine an observer who just follow all the quantum branches, but it wouldn't be an observer like us, because what seems to be a core feature of observers like us is that we believe we have a single thread of experience. And to maintain that belief, our process of observation must equivalence all the different quantum branches. How much effort will that be? Well, inevitably, if a thread of history branched, our equivalencing has to undo that branching. And that suggests that the number of elementary equivalencings will have to be at least comparable to the number of elementary branchings, making it seem that the effort of observation will tend to be at least comparable to reduction of effort associated with parallelism in the underlying quantum process. In general, it's interesting to compare the effort of observation with the effort of computation. With our concept of elementary equivalencing, we have a way to measure both in terms of computational operations. And yes, both could in principle be implemented by something like a Turing machine, though in practice the equivalencies might be most conveniently modeled by something like string rewriting. And indeed, one can often go much further, talking not directly in terms of equivalencies, but rather about processes that show attractors. There are different kinds of attractors, sometimes as in class 1 cellular automata. There are just a limited number of static global fixed points, say either all cells black or all cells white. But in other cases, such as class 3 cellular automata, the number of output states may be smaller than the number of input states, but there may be no computationally simple characterization of them. Observers like us, though, mostly seem to make use of the fixed points. We try to symbolicize the world, taking all the complexities out there and reducing them to discrete conclusions that we might, for example, describe using the discrete words in a language. There's an immediate subtlety associated with attractors of any kind, though. Typical physics is reversible in the sense that any process, say two molecules scattering from each other, can run equally well backwards and forwards. But in an attractor, one goes from lots of possible initial states to a smaller number of attractor final states. And there are two basic ways this can happen, even when there's underlying reversibility. First, the systems one's studying can be open in the sense that effects can radiate out of the region one's studying. And second, the states of the system that the system gets into can be complicated enough that, say, a computationally bounded observer will inevitably equivalence them. And indeed, that's the main thing that's happening, for example, when a system reaches thermodynamic equilibrium, as described by the second law. And actually, once again, there's often a certain circularity. One's trying to determine whether an observer has finished observing and come to a conclusion, but one needs an observer to make that determination. Can we tell if we finished forming a thought? Well, we have to think about it, and in effect, by forming another thought. Put another way, imagine we are trying to determine whether a piston has come to a conclusion about pressure in a gas. Particularly if there's microscopic reversibility, the piston and things around it will continue wiggling around. It'll take an observer to determine whether the heat is dissipated to the point where one can read out the result. But how do we break out of what seems like an infinite regress? The point is that whatever mind is ultimately forming the impression that is the observation is inevitably the final arbiter. And yes, this could mean that we'd always have to start discussing all sorts of details about photoreceptors and neurons and so on. But as we talked about at length, the key point that makes the general observer theory possible is that there are many conclusions that can be drawn for large classes of observers, quite independent of these details. Okay, but what happens if we think about the raw Ruliad? Now all we have are EAMs and elementary events updating the configurations of them. And in a sense, we're fishing out of this pieces that represent observers and pieces that represent things they're observing. Can we assess the cost of an observation here? It really depends on the fundamental scale of what we consider to be observers. And in fact, we might even think of our scale as observers, say measured in terms of EAMs or elementary events, as defining a fundamental constant of nature, at least for the universe as we perceive it. But given this scale, we can, for example, ask for there to develop consensus across it, or at least for every EAM in it to have had time to communicate with every other. In an attempt to formalize the cost of observation, we'll inevitably have to make what seem like arbitrary choices, just as we would in setting up a scheme to determine when an ongoing computational process has generated an answer. But if we assume a certain boundedness to our choices, we can expect that we'll be able to draw definite conclusions and in effect be able to construct an analog of computational complexity theory for processes of observation. The future of observer theory. So my goal has been to explore some of the key concepts and principles needed to create a framework that we can call observer theory. But what I've talked about here is just the beginning, and there's much still to be done in fleshing out the theory and investigating its implications. One important place to start is in making more explicit models of the mechanics of observation. At the level of the general theory, it's all about equivalencing. But how specifically is that equivalencing achieved in particular cases? There are thousands of kinds of sensors, measuring devices, analysis methods, and so on. All of these should be systematically inventoried and classified. And in each case, there's a meta model to be made that clarifies just how equivalencing is achieved and, for example, what separation of physical or other scales makes it possible. Human experience and human minds are the inspiration and ultimate grounding for our concept of an observer. And insofar as neural nets trained on what amount to human experiences have emerged as somewhat faithful models for what human minds do, we can expect to use them as a fairly detailed proxy for observers like us. So, for example, we can imagine exploring things like quantum observers by studying multi-way generalizations of neural nets. And this is something that becomes easier if instead of organizing the data into real number weights, we can atomize neural nets into purely discrete elements. Some investigations of potentially realistic models provide a useful practical grounding for observer theory. But to develop a general observer theory, we need a more formal notion of an observer. And there's no doubt that a whole abstract framework, perhaps using methods from areas like category theory, that can be developed purely on the basis of our concept of observers being about equivalencing. But to understand the connection of observer theory to things like science, as done by us humans, we need to tighten up what it means to be an observer like us. What exactly are all the general things we believe about ourselves? As we talked about, many we so much take for granted that it's challenging for us to identify them as actually just beliefs that as just beliefs that in principle don't have to be that way. But I suspect that the more we can tighten up our definition of observers like us, the more we'll be able to explain why we perceive the world the way we do and attribute to it the laws and properties we do. Is there some feature of us as observers, for example, that makes us parse the physical world as being three-dimensional? We could represent the same data about what's out there by assigning a one-dimensional space-filling coordinate to everything, but somehow observers like us don't do that. And instead, in effect, we probe the Ruliad by sampling in what we perceive are 3D slices. And yes, the most obvious coarse graining just considers progressively larger geodesic balls, say in the spatial hypergraphs that appear in our physics project, but that's probably at best just an approximation to the sampling observers like us do. As part of our physics project, we've discovered that the structure of the three main theories of 20th century physics, statistical mechanics, general relativity, and quantum mechanics, can be derived from properties of the Ruliad just by knowing that observers like us are computationally bounded and believe we're persistent in time. But how might we reach, say, the standard model of particle physics with all its particular values of parameters and so on? Some may be inevitable given the underlying structure of our theory, but others, one suspects, are in effect reflections of aspects of us as observers. They are derivable, but only given our particular character or beliefs as observers. And yes, presumably things like the constants of nature that characterize the particular constant of nature that characterizes our size in eames will appear in the laws we attribute to the universe as we perceive it. By the way, these considerations of observers like us extend beyond physical observers. So, for example, as we tighten up our characterization of what we're like as mathematical observers, we can expect that this will constrain the possible laws of our mathematical universe. We might have thought that we could pick whatever axioms we want, in effect sampling the Ruliad to get any mathematics we want. But presumably observers like us can't do this, so that questions like, is the continuum hypothesis true, can potentially have definite answers for any observers like us and for any coherent mathematics that we build. But in the end, do we really have to consider observers whose characteristics are grounded in human experience? We already reflexively generalize our own personal experiences to those of other humans. But can we go further? We don't have the internal experience of being a dog, an ant colony, a computer, or an ocean. And typically, at best, we anthropomorphize these things, trying to reduce the behavior we perceive in them to elements that align with our own human experience. But are we as humans just stuck with a particular kind of internal experience? The growth of technology, and in particular sensors and measuring devices, has certainly expanded the range of inputs that can be delivered to our brains. And the growth of our collective knowledge about the world has expanded our ways of representing and thinking about things. Right now, those are basically our only ways of modifying our detailed internal experience. But what if we were to connect directly and internally into our brains? Presumably, at least at first, we'd need the neural user interface to be familiar, and we'd be forced into, for example, concentrating everything into a single thread of experience. But what if we allowed multi-way experience? Well, of course, our brains are already made up of billions of neurons that each do things, but it seems to be a core feature of human experience that we concentrate those things to give a single thread of experience. And that seems to be an essential feature of being an observer like us. That kind of concentration also happens in a flock of birds, an ant colony, or a human society. In all these cases, each individual organism does their thing, but somehow collective decisions get made with many different situations getting equivalents together to leave only the final decision. So that means that from the outside, the system behaves as we would expect of an observer like us. Internally, that kind of observer behavior is happening above the experience of each single individual, but still at the level of the hive mind, it's behavior that's typical in an observer like us. That's not to say, though, that we can readily imagine what it's like to be an observer like this, or even to be one of its parts. And in the effort to explore observer theory, an important direction is to try to imagine ourselves having a different kind of experience that we do. And from within that experience, try to see what kind of laws we would attribute, say, to the physical universe. In the early 20th century, particularly in the concepts of relativity and quantum mechanics, it became clear that being more realistic about the observer was crucial in moving forward in science. Things like computational irreducibility, and even more so, our physics project, take that another step. One used to imagine that science could somehow be fundamentally objective and independent of all aspects of the observer. But what's become clear is that it's not, and that the nature of us as observers is actually crucial in determining what science we experience. But the crucial point is that there are often powerful conclusions that can be drawn even without knowing all the details of an observer. And that's a central reason for building a general observer theory, in effect to give an objective way of formally and robustly characterizing what one might consider to be the subjective experience in science. So that's what I wrote about observer theory. And I said at the end there, no doubt lots of precursors of varying directness that can be found for the things I was talking about. I haven't attempted a serious historical survey. I thought that would be an interesting thing to do. In my own work, Chapter 10 of A New Kind of Science from 2002 is entitled Processes of Perception and Analysis, and really was for me sort of the precursor of these efforts. So let's see. Well, I'm happy to try and take, if I have a chance here, a few questions, perhaps. Mike asks, how does observer theory get us behind consciousness? Oh, let's see. Where does it meet it? Well, I think the question is sort of what's the essence of what's happening in consciousness? How is what happens in a brain different from what happens in generic computation? I think what I've increasingly realized is that we might have thought that consciousness was sort of the tippy top of all kinds of processes in the universe. But I don't think that's true. I think many processes in the universe are doing sort of arbitrarily sophisticated computations, but actually the things that happen in our brains are in some sense specific kinds of computations, in particular kinds of computations where we're doing the thing that is central to observer theory, which is we're taking sort of the complexity of the world and we're kind of crushing it down so that we believe we have a sort of single thread of experience. I think that's important to our kind of perception of consciousness. I mean, we can talk about I mean, there's certainly a link between sort of the idea of consciousness and the kind of concept of observers. I think what I'm trying to do with observer theory is to essentially take a scientific slice of what we need to talk about consciousness, the scientific slice that we need to make conclusions about things, general things about how we perceive the world, rather than considering the internal experience of doing that. We're considering sort of what kinds of internal experiences can we have that we can kind of identify scientifically. Hattori asks, would you say that an observer is made recursively by sub-observers? Oh boy, that's an interesting question. I mean, there's a certain circularity to an observer has to know that you have a thing that's an observer that's come to a conclusion about what they see. One sort of has to have another observer observing that. And I don't know whether I would consider that sort of a sub-observer. I think that for us, we have this series of distinct thoughts, and a thought doesn't have other thoughts inside it particularly. A thought, we at least feel, is like a thing unto itself. A word is a word. The word doesn't have other words inside it. So I think there's a sense in which there's sort of the question of defining the observer depends on sort of other observers. It's kind of a network of observers that all have to be consistent to define the notion of observer. But I would say that there is a sense in which there is a sort of a distinct kind of discreteness to the kind of notion of an observer itself. Let's see. Well, Soren is asking about the second law, which states that the entropy is increasing along with the expansion of the universe that will lead to the death of everything. Well, let me just say one thing quickly about that, which relates to observers. You know, the second law essentially is saying that the configuration of molecules that we get, we can't recognize as being ever anything different from random. Even though in reality, there is a precise configuration of molecules that we could reverse the dynamics on and get back to whatever initial condition we had. But the point is that observers like us can't do that. So, for example, when we think about the future of the universe and sort of the idea of the heat death of the universe, there is a configuration of molecules that is the universe today. Its distant future might be something in which those molecules are bouncing around in some particular way, which to observers like us today looks like random heat. But we can certainly imagine observers who would notice, oh, those molecules are configured in this or that particular way. That was the thing which was the result of what happened in 2025. And now we're a trillion years later on. And this is how things played out from that. Observers like us, who are computationally bounded, for example, we can't recognize all that stuff. A trillion years from now, we'll never be able to invert the computation to say that was what happened in 2025. But it isn't to say that information is not there. It's there, but not to observers like us. So the story of the second law and these phenomena like the heat death of the universe is really a story of observers like us and a story of the fact that observers like us believe that the best we can do is to say things got more random or entropy increased. So in the traditional sort of treatment of the second law, by the early 20th century, people were talking about coarse graining and the idea that this precise details of molecules, you sort of couldn't see that. And there was some kind of notion of that the things you could prepare or observe about gases were coarse-grained versions. That was never very well defined. What was a valid coarse graining? Why couldn't you have a coarse graining that very particularly picked out the particular things that happen in a gas of this or that kind? What this kind of computational point of view and observer theory kind of gives one is a way to be more formal and precise about what it means to what kinds of coarse graining are conceivable coarse grainings, because it tells you that the coarse grainings that you can do are ones that correspond to computationally bounded observers. And that means that you actually have the chance to really prove something about the fact that the dynamics of molecules is doing enough irreducible computation that's sort of encrypting the initial condition to the point where observers like us, with our computational boundedness, can't decode it. So it's no longer just, oh, well, there is this coarse graining. We have to kind of be vague about what that means. It's the coarse graining is associated with the fact that observers like us have this very particular property of being computationally bounded. Let's see. Sandeep asks, it's not clear when I'm saying that do humans, or for that matter, everyone in the universe sample the Ruliad in the same way, or does every individual sample it differently? So I think every mind is effectively at a different place in the Ruliad. Minds can communicate by essentially sending signals, sending things like particles, things like concepts, which are sort of the analog of particles in Rulial space, from the position of one mind in the Ruliad to the position of another mind. So just as human minds occupy in physical space different places, so also they occupy different places in Rulial space. They have different views of the rules that govern the universe because they're configured in different ways, their brains work differently, and so on. So the idea is that that every mind is at a different place in Rulial space. Human minds, particularly ones with sort of common backgrounds, are pretty close together in Rulial space. You can move in Rulial space by kind of changing your way of thinking about things. But this is, every mind is at a particular place in Rulial space. So human minds form this little clump somewhere in Rulial space. Cat minds, dog minds form other clumps. And this question, the interesting thing is because the clump, the flock of human minds in Rulial space is very tightly, is very sort of tight relative to all of Rulial space. There are many things about the universe that we all kind of agree about how it works. We all kind of agree that space is three-dimensional, for example. That's in a sense because we are tightly clumped in Rulial space. If we could imagine if there was another mind that was far, far away that thought about the universe in a different way, it might think about the universe as one-dimensional. It might think about something very differently. The thing is that as a practical matter, as a matter of historical contingent, we are all close together in Rulial space, just as we are all relative to the span of the universe close together in physical space. And I think that's if we imagined an entity far away in Rulial space, its perception of the universe would be very different. Its laws of physics, its perceived laws of physics might be very different. The problem is it's very hard for us to communicate with something far away in Rulial space. It's hard enough to communicate with something far away in interstellar space and physical space. It's harder, perhaps still, to communicate with something that is far away in Rulial space, that has a very different way of thinking about the way the universe works and so on. It's sort of, that's the, in a sense, the problem of searching for extraterrestrial intelligence is not just, are the extraterrestrials sort of nearby in physical space, but also how far away are they in Rulial space? And systems that are far away in Rulial space, we'd look at them and say, well, they're doing something complicated. We don't really know what it is. Are they really intelligences? Well, unless they're close enough in Rulial space that we can kind of align our way of thinking about things with their ways of thinking about things, we won't identify them as being intelligences like us. And I think that's sort of the fundamental feature of extraterrestrial intelligence is there are lots of physical processes in the universe which are complicated and which are kind of as complicated as the kind of the nerve firings in our brains, but which we don't identify as being sort of aligned, close enough to us in Rulial space, aligned with us in what they do to be able to say that, this is an intelligence like us. Um, Super Crunch says, show love to the observer. Well, yes, I should thank you all for being observers of my efforts to understand observers. Uh, Yao asks, why do observers exist? That's a very good question. It's a, I think the interesting thing about the Ruliad is the Ruliad necessarily exists. Once you have the idea of computation, the Ruliad is an inevitable construct and a unique construct. Now, why should observers like us exist within the Ruliad? It would be nice to be able to prove that observers like us must exist within the Ruliad, to prove as a matter of science that we must exist. It gets very theological very quickly because in a sense, the Ruliad is out there necessarily existing. People have often talked about, is there a necessary being, which they would identify at different times with God or various other kinds of things like that. And it's kind of the Ruliad is a necessary thing. What is contingent is our existence within that. And as I say, the thing that's sort of exciting about thinking about the Ruliad and thinking about these things computationally is one might imagine that one could just outright prove that somewhere in the Ruliad there must be observers like us. What would it take to do that? Well, one feature of observers like us is there are lots of us. If there was just one of us, one mind, then it would be hard. Many of the things that we kind of think about the universe and so on wouldn't really have the same grounding if there was just one mind. We have a sort of collective way of thinking about things where we convince each other that there is an objective reality, that we're all seeing the same things, that there is something to discuss about objective reality. If there was just one mind in the universe, we wouldn't really have that option. So one of the things that's interesting, I think, and surprising about observers like us is there are lots of us. And so the question of whether there inevitably have to exist observers like us with lots of us starts reflecting on things that seem very specific, like ideas about life and self-reproduction and so on. Self-reproduction is important because it makes a bunch of observers that are all kind of the same. And although not exactly the same, they start from the same place, but then their minds can evolve differently. So I kind of think that the very interesting thing that again, more progress needs to be made on is this question of can one prove that within the Ruliad there inevitably will be sort of constructs that have certain forms? I'm sure the answer is yes, but making that proof will be a very interesting thing to do. And by the way, if you make that proof, kind of the bonus point is you might get to understand the density of such objects in the Ruliad, or in effect, the density of extraterrestrial intelligences or extra, I don't know what one calls it, extra mental intelligences or something that are away from that. It's kind of the density in Rulial space of intelligences or of things that are observers like us, so to speak. So that's the thing that will be the big bonus point in being able to derive our existence from all of this, is that we might be able to know the density of the existence of things a bit like us. But yes, it's a very good question. Why do observers exist? That is something that can be scientifically addressed. And I sort of started poking around at that, although I can't say I've solved it. Again, I think it enmeshes quite a lot with things about the origin of life, the idea of self-reproduction and so on, which I hadn't expected. I had thought that a question like why do observers exist is a question that would be sort of not as specific as to start talking about things like life and self-reproduction, but I think it actually does entangle with this. Let's see. Brady is asking, so an ocean is not an observer because it's not equivalencing anything. I think that observers like us, it really is important to brains that we conclude definite things about what to do. I realized recently that the first things that had brains in the history of biology were when animals were around. Plants that just sit in one place don't have brains in the same way. As soon as you have an animal that's got to move around, the animal is in a definite place. It walks left, it walks right, it walks forwards, it flies up and down, whatever. It's in a definite place. And so one thing that has to happen is it takes all that sensory input, millions of different senses that it might have, and somehow it has to decide because it needs to be in a definite place. So it has to take all that sensory input and it has to say, I'm coming up with a definite conclusion. I'm going to turn left. And so that phenomenon that was sort of born of the idea of animals and the idea of things that were living that could move around, I think that idea is what led to this notion of a single thread of experience that we have, which to us seems like it couldn't be any other way. But in a sense, it's a consequence of the fact that we had to make definite decisions. And now that's a thing that I think is specific. That's a thing that needs to be true to have an observer like us. And so I don't think something like an ocean, I haven't really thought that through properly, but I don't think that has that same kind of concentrating down of things into sort of a definite conclusion. One part of the ocean gets to a different thing than another part of the ocean. Just like one part of our brain is thinking about one thing, another part of our brain is thinking about another thing. It's, but in the end, let's say one says a definite thing. One part of my brain might be thinking about the fact that it's getting close to dinner time or something. Another part of my brain might be thinking about some other thing about the computer system that I'm sitting in front of or something. But in the end, I'm going to say some definite word next. And that's how brains like ours work. Let's see. Yeah, asks, so everything is just the execution of instructions. Are we inside a while true kind of programming construct? I think at some level we are. And I think that at some level we do definite things. We have, 250 actuators or something of our fingers moving and our voice box moving, our vocal cords moving, and so on. And we send signals, we make definite things happen. That's the stream of instructions that we are imposing on the world. And although we get lots of sensory input, in the end, it's all turning into the what we do next type series of things, which I suppose one could think of as a pretty discrete series of instructions. I mean, I think we're going to understand this better as we get towards kind of really smooth humanoid robotics, really connected to good sort of AI-ish things. I think we'll have more of an intuitive sense of what's going on there, of the stream of sensory input going through to the stream of instructions about move this finger this way and so on. Let's see. EJ asks, does the observer necessarily have to be conscious, or could an observer ultimately be viewed as a representation, a model of measurement? Let's see. So this question of, okay, ultimately what matters to us is what we perceive. We have devices, measuring devices, that sort of prep what it is we'll receive. We could receive the raw data. Let's say we're measuring the pressure of a gas. we could receive, on our fingers or something, the raw data of what, how all the molecules are moving around. But rather, we have a measuring device that aggregates that for us and just as a pressure gauge that has some sort of display or something on it. The uh, it's So I think that it's kind of this idea of concentrating things down to get a definite answer. This is all a story of observers. Whether those observers, in the end, those observers are implemented in our brains, but we can absolutely prep them with with uh, with measuring devices. And so it is an important thing that measuring devices go from the complexities of the world to individual numbers about what the pressure of something is, or some such other thing. So I think it's really the same kind of thing. And with measuring devices, they're a bit easier than brains to take apart and see how the measuring device really works. And yes, that's a perfectly reasonable thing to be studying, and that's a thing to which this observer theory that I'm talking about, with all these notions of equivalencings and so on, applies. Let's see. I don't understand this last comment that I have listed here from Acetatum. Since the future is our audience, does it have any effect on us? Oh, I see. I see. Let's think about that. So if the future is what will receive the effects, the things we do will play out in the future. The decision to do a particular thing will have consequences for the future. How much, how little, who knows? But the event that happens now will have consequences in the future. And there's sort of a question, I suppose, of how to think about the consequence, what that thing that happens in the future, how will it play back on what happens to us now? I'm somewhat reminded of the movie Arrival. Okay, this is a bit of a spoiler for people who haven't seen it, which I happened to do some consulting on a decade or so ago when it was being made. That has kind of a notion of critters, spoiler alert, that whose view of time is different from ours. And instead of thinking of time as something where we progressively kind of live into the future, it's a notion that sort of that all of time is laid out before us. And so in a sense, our future can affect our past because we're thinking of all of time laid out before us. It's kind of an interesting thing when we think about the Ruliad. The Ruliad is this necessary object that has all of these computational processes in it. And we normally think about ourselves as kind of progressing through time. Time, as far as I'm concerned, is the progressive doing of computation in the universe. The passage of time is the progression of computation in the universe, the computing of the next state of the universe from the previous one. That's what the progression of time, the passage of time is. That's our usual impression. But with the Ruliad is a bit strange because the Ruliad, we say the whole thing is just a necessary object. So in a sense, all of time already exists in this thing that is the Ruliad. So how is that consistent with our impression that we only progressively uncover the future? Well, the thing is that the way we can think about it is it's a computationally bounded observer story. Because yes, the whole Ruliad is out there. There is a sense in which all of time already exists in the Ruliad. However, as computationally bounded observers, we only get to crawl one little tiny bit through the Ruliad, as that our sort of computational boundedness prevents us from sort of sweeping out and seeing much more of the Ruliad. We're stuck observing little tiny pieces of the Ruliad. And that's the sense, that's a sense in which we can think about the progress of time, is it already all exists. And we're just crawling through it one step at a time, you might say. That's one view. The other view is we build the future progressively as by doing computation. So in other words, instead of thinking of the Ruliad as already existing, we think of it as being created by the actual doing of computation. These are equivalent views, in physics, in sort of quantum physics and so on. These will be like the Schrodinger picture and the Heisenberg picture of quantum mechanics. That's not particularly useful unless you happen to know that formalism. But it's kind of a question of what's changing, the world or the observer, so to speak. and that's sort of the correspondence between those things. But it's so in that sense, the sort of what is now and what is the future is inevitably connected. And it's a deterministic thing in a sense, what the future is. And so you could say, well, the future affects the past because look at that thing in the future. We can know from that thing in the future what must have happened in the past. For example, if you see the thing that, a thing that's smashed on the floor, you can say, well, it's pretty likely that you see some light bulb, if those even exist anymore, that sort of fell on the floor and smashed. You could say, well, that probably its past was that that was its future. Its past was it must have fallen and broken. So just as one might say as well, if we see this thing, we're dropping this thing, we can say we predict its future, it will do this or that. But I think so. Uh, there's always this question. It's a tricky philosophical question. The question of whether things happen because of the mechanism by which they happen, or whether things happen because they achieve something, they achieve a purpose by happening. This is something that comes up a whole bunch in biology, a little bit less in physics, although it does happen in physics as well, because in physics, we can say there's a law of motion, Newton's law, something like this. There's an alternative formulation that came 150 years after Newton's laws, which is the principle of least action, which says, instead of just saying at every moment the thing moves according to forces that are applied to it, it says the whole motion of the thing will be such that it minimizes or extremizes this action object, which is some calculable thing, something that represents some feature of motion. So that's by saying it is trying to achieve the least action. That's an alternative to saying it is doing what it does because it was poked by these forces. There's a version of the principle of least action, which is the principle of least time for light. Light goes through the path that takes the least time. That is one way of describing it. Another way of describing it is, oh, the photons have this momentum and they're sort of deflected in this way, and they go in this way according to a mechanism. And in the case of light, those are sort of a little bit equal. They're both reasonable formalisms. And I would say in physics as well, the least action principle is useful for some things. The other one is sort of the more elementary approach. But this question of what thing that happens is best described by is best described by mechanism, and what is best described by purpose. And I think that's an interesting thing. I wrote recently about sort of the meta-engineering that you can do from the game of life cellular automaton, its 50-year history and so on, where it's sort of a question of whether you say, this weird configuration that we got here is this way because somebody figured out they would do this cool thing, or is it this way because we just ran the search and this is what came out? Or is it this way because it achieves a certain purpose, or is it just this way and it's going to do certain things? And in biology, there's a great tendency as a result of kind of theory of natural selection and so on to say, the beak of the finch is that shape because it is good for poking out this kind of fruit or something, where instead of the beak of the finch is that shape because some diffusing morphogen caused the growth process for the beak to do this or that thing. And I think it's an interesting thing. I've just been thinking about it recently, kind of the comparison between explanations by purpose and explanations by mechanism, which is somewhat similar to sort of asking how much does the future affect the past. An explanation by purpose is like saying what you're talking about the thing in terms of what it will achieve, so to speak. I mean, I think Aristotle had this, who liked making lists of things, had these lists of causes, and had this kind of idea of final cause, the teleology, the purpose of the thing, as opposed to its what are the others? The formal cause and things, the form of the thing, but more this sort of this comparison between mechanism and purpose, as a way of explaining things. And it's been difficult because mechanism is something we really get to explain in terms of we get formalizations of mechanism, computational rules, formalized mechanism. It's been difficult to compare purpose and mechanism because we haven't had a good way to formalize purpose. And actually, I've sort of tried to understand how one would do that using essentially the kind of symbolic language ideas, computational language ideas from Wolfram language and so on. I think we're getting closer to being able to reasonably generally formalize purpose. And by the way, that's not completely unrelated to observer theory, because observer theory has to do with, so what did you actually get in the end? And that's quite related to the question of what did you want to get out of it in the end, so to speak. But I think that will allow us, it's a formalism still has to be built, that will sort of allow us to make comparisons of explanations by mechanism, explanations by purpose, and we'll be able to say things like, in this particular case, with this configuration of pixels or whatever, this is more succinctly explained by purpose than it is by mechanism. Now, needless to say, the language of explaining by mechanism will have to be compared to the language for explaining by purpose. In what I imagine, there'll be sort of the same language, but one will be using, if one's descriptive elements will be different for mechanism and purpose. But so one gets to be able to ask questions like, did this seem like it was made on purpose? Because its description in terms of purpose is much smaller than its description in terms of mechanism. Or did this just happen? And so it is really described in terms of mechanism. So that's a few thoughts about kind of the sort of thinking about the future, so to speak. All right, maybe one last comment question here. Harry asks, so the Ruliad, is it finite or infinite? It is countably infinite. So it's like the integers. It's like there are an infinite number of integers, but you can distinguish every integer. Unlike the real numbers, where it's kind of where you can go in between any two real numbers, there's another real number. It's got a different level of infinity. But the Ruliad is a countably infinite object. Let's see. So I think the questions here about is what one's talking about with the Ruliad and so on some strange and sciencefied form of religion? That's an interesting question. I think what is kind of intellectually sort of exciting about some of these things is that there've been a certain set of questions that one has been able to address with science, with modern science, as it's evolved since the 1600s. There were plenty of questions that already existed that have been discussed by theologians for, a couple of thousand years before modern science came along. Modern science said we can do these particular things. And so those are the things that got concentrated on and were the things that allowed us to build technology, all those kinds of things. But it is interesting that with the developments that we have in science now, kinds of things I've been trying to think about, we get to go back to some of these questions that got asked by theologians for a long time and maybe have some scientifically relevant things to say about them. I think it's a question of sort of religions tend to have both sort of deeper philosophical points and what one could perhaps crassly call sort of a retail presence, so to speak. And I think that's this is on the deeper philosophical side. But if you ask questions like sort of our place in the universe and the purpose of the universe and things like this, those are things for which we have something scientific to say. Now, how does it affect the leading of one's life that that one can think about the Ruliad and one can think about sort of the space of all possible minds and so on? I'm not sure. I've wondered about that quite a bit. In other words, what things, should one lead one's life differently given that one knows these things about the world? I think the one conclusion that I would come to, which is more of an intellectual conclusion, is that there are deep foundations of things. It is worth thinking foundationally about things because there are deep foundations of things. things are not just the way they are because they happen to be that way. The things are the way they are because there are deep foundations that lead them to be that way. And I think that that's a sort of a life lesson from some of the science, is it's worth trying to think foundationally about things, which is not something that, for example, in many cases, sort of modern education tends to sort of direct things in these very specialized, specific areas. And that tends to be sort of the antithesis of foundational thinking. And I think that one of the things one learns from the science is that there really are deep foundations, and it's worth thinking about things in a foundational kind of way. I think uh, I I will tell some silly story perhaps to end, which is we're visiting some country with a couple of my kids, and this is a country where in the the immigration or the entry sort of information, you have to fill out, among other things, you have to fill out religion. And so I was considering checking the box that said animism. And my kids said, don't do that. We'll be stuck for hours, in passport control if you do that. So I didn't do that. But the I think it's an interesting thing when one sort of, again, I don't really know how, one of the things about sort of religions is they suggest things about how to lead one's life. I have strong opinions about that, but I don't think they're derived specifically I don't think they derive from kind of the sort of philosophy that I've understood from thinking about sort of these foundational questions about the way the world works. I mean, I have to say that one of the things that perhaps is an irony in my life is that these things that I talk about the Ruliad and about sort of the computational foundations of everything, are in a sense deeply deconstructive of the world. They're taking sort of the particulars of they're trying to generalize far, far away from the particulars of our human existence, so to speak. And for a while, I was kind of like, it's surprising because as a person, I'm a person who finds people interesting. I'm sort of into the idea of people. And yet in science, I seem to be doing these things that are coldly not considering the people involved, that are coldly thinking about sort of the raw science in a way that's deeply deconstructed from the particulars of kind of human experience. But the irony for me is that having built all of that science that's sort of deeply deconstructed and sort of very general and austere, it's turned out in recent years that that I've realized that the observer, that's us, is actually critically important to those things which I had thought were just pure austere science, like the laws of physics and so on, that I've realized that actually it isn't true that the laws of physics are cold and austere and very non-human. The laws of physics critically depend on the fact that it's humans who are perceiving them. And so, in a sense, even though I had thought, it's kind of one of my principles about doing science is to kind of let the chips fall as they do. Even if one has the prejudice that humans are a significant thing, you just do the science. And if the science is kind of leading you in a direction where humans aren't important, well, you do that anyway. And it's sort of been an interesting irony in my life, at least, that in the end, from having built this thing that is sort of austere, deconstructed science, one comes back to realizing that actually us humans really are more important, really are critically important, even in thinking about that austere kind of way of talking about science. And it is certainly an interesting question about sort of the relationship to theology and religion and so on, the extent to which these sort of philosophical conclusions map onto things that people have been saying for thousands of years. And I would say that I have found that interesting to study. It is so difficult. The sort of relationship between the things that I think about and the kind of historical antecedents and relations is difficult for me. I mean, in terms of raw science, I have often studied scientific history, whether it's about the second law of thermodynamics or something else. That history is hard in and of itself, but it has a certain definiteness to it. You can just say, this person observed this gas, wrote down this formula, and so on. It has a way of being anchored. I found the history of philosophy vastly more difficult. and the history of kind of religious thought also more difficult, because one's really dealing with things where instead of being able to say, well, they wrote down this formula, it's like, well, they had this statement made in a language that I don't know that seems to roughly say this, that in their way of thinking about things 2,000 years ago might have resonated in this way, but in our way of thinking about it today, it feels completely different in what's being said. And so I found it very difficult to really feel confident in sort of talking about how the things that I'm thinking about relate to things that people have thought about in those ways before. And doesn't help that one grows up in a certain, in my case, in sort of a standard Western kind of tradition. And there are things which to other people are sort of obvious because they grew up in that tradition. It takes a big effort to kind of, map one's mind into those kinds of things, even if in fact the science that one's built, which I feel I understand reasonably well, might have sort of resonances with those kinds of things. And okay, we should probably wrap up there, but uh, thank you for being here, and I look forward to talking about other things at another time. Thanks so much, and bye for now.